All right, for our second set of notes for the day, we're looking at conditional probability. I also want to point out that we have two more sets of notes before our first exam, so expect your first test to be sometime next week. So make sure you're looking at these homework problems and make sure you're understanding what's going on. So before we get started, we're just talking about conditional probability, and conditional probability is when we are looking at the probability of an event happening given that another event has already occurred. And you can see the definition right here. It's the probability event B occurs given that event A occurs. That's called the conditional probability, and it's noted as P parentheses B, and then there's that vertical line A. So that's the probability that event B given the probability of event A. And A is going to be the event that is given. And hopefully the examples will kind of clear that up. So the first thing that we're looking at, we have a fair die is rolled once. There are 6 equally likely outcomes, 1, 2, 3, 4, 5, and 6. We're going to let F be the event that a 5 is rolled, and then we're going to let O be the event that the dice comes up odd. So find the following probabilities. Well, the probability for F, which is the event that a 5 is rolled, is really quite simple. There's only one 5 on a single die. So the probability of event F is 1 in 6, which is going to be approximately 0.167. And that's our probability for A. Now, the probability for for the second event, though, is the probability of F given O. So we're given that the number is odd. What's the probability that it's a 5? Well, on a single die, there are only 3 odd numbers, 1, 3, and 5. So we're given that the number is going to be odd. What's the probability that that number is a 5? That's what this notation means. So the probability of that the number is a 5, given that the numbers are all odd, is 1 out of 3, which is 0.333. And then finally we have part C, it's the probability that the number is odd, given that it's not a 5. So given that it's not a 5, let's look at it. Let me write out the numbers on a die. 1, 2, 3, 4, 5, 6. Given that it's not a 5, so we're taking 5 completely out of the mix. What's the probability that it is odd? Well, that only leaves us with 1 and 3 as our remaining odd numbers. So the probability that it is O, not F, given not F, I should say, is 2 out of 5. There's 2 odd numbers remaining out of the 5 possible numbers left once we eliminate 5 from the mix, and that's going to be just 0.4. That's our probability. So there's kind of a quick overview of what conditional probability looks like, and we're going to see that here again in a second example, and hopefully this kind of make a little bit more sense as we progress through all the examples. So for example 2, it says that the table shows the age and rank of faculty members at a university. Suppose that a faculty member is selected at random. Determine the probability that the selected faculty member is in their 50s. So we're only interested in a faculty member being in their 50s. So when we look at our table of values, right here is the box indicating, or this is the row for faculty members in their 50s. We're not interested in any other information other than that these people are in their 50s. So if we go all the way across, we have our total, which is 253. So 253 out of the 1,164 faculty members is the number of faculty members that are in their 50s. So for part A, we're looking at the probability, and I've given these all different labels. I have A sub 1, A sub 2, A sub 3, A sub 4. We're looking at the probability that the individual is in their 50s. That is 253 faculty members out of the 1,164 total members, which is 0.217. So there's a 21.7% chance that a randomly chosen faculty member will be in their 50s. Now, part B is different because it says determine the probability that a selected faculty member is in their 50s given that an assistant professor is selected. So assistant professor is this column right here. And basically what we're looking at now is we're looking at the person being in their 50s given that they are an assistant professor. So the notation would be probability of A sub 4 given that they are an assistant professor, and that again is the notations that you see across the bottom here. So there are 320 assistant professors, and of those 320 assistant professors, only 36 are in their 50s. So our probability in this case is 36 out of 320, which is 0.113 or 11.3% of the assistant professors are in their 50s. So that's how the conditional probability works. We have to take into consideration certain aspects of the dynamics that we're looking at, and then we can simplify it and come up with these probabilities. So the conditional probability rule, previous two examples, we computed the probabilities directly, meaning that we first obtained the new sample space determined by the given event. As we did with the professors, we just simply narrowed it down to assistant professors only. Then we looked at the probabilities. But sometimes we cannot compute these probabilities directly. We have to compute them in terms of unconditional probabilities. And we're going to see that here in the next example. And with this particular example, we're referring back to the professors or the faculty members at the university. We use direct computation to determine the conditional probability that a faculty member is in their 50s given that an assistant professor is selected. So we restricted everything as we did in the previous example, and we came up with 0.113. Now we want to express that conditional probability in terms of unconditional probabilities. So what does that mean exactly? So we have the probabilities that, let me write this out. Let's consider the probability that the individual is an assistant professor and they are in their 50s. So that's the notation from our previous example. There are 36 professors that are in their 50s, and there is a total of 1,164. Sorry, I got distracted. I just got a call. Our goats had more babies. Well, actually, I take that back. Rachel called Carla and told her, actually FaceTimed her and told her about goats having babies. And then I get a secondary phone call. Nobody cares about me. Let's see. So what was I saying? Okay, so the probability that the individual is a assistant professor and they are in their 50s. Well, there's 36 individuals that are professors, assistant professors in their 50s. And there's a total of 1,164 faculty members. So that probability is 0.031. Then we look at the probability that they are an assistant professor. So we're only now focused on the probability of R sub 3, which is 320 assistant professors out of the 1,164 faculty members. And we get a probability of 0.275. So from the previous three probabilities now, what we have is the probability that A sub 4, given that they are an assistant professor, is going to be 36 out of 320. And if we notice from the notation that we've used in these two calculations, we could have 36 over 1164 over 320, if I can write. Wow. We'll get this right. 320 out of 1164. And just through basic algebraic steps, the 1164s will cancel. We're left with 36 over 320. And we have now computed the general formula for conditional probability. You're not going to have to do any problems like this where you generate the conditional formula or the formula. I'm just showing you that this is what we end up with. So if we wanted the probability of B given A, it's the same as the probability of A and B divided by the probability of event A. And that's what we did right here in this third example. I think it was the third example. Yeah, it was. So now let's try to apply some of these. So example 4. From America's Families, and I believe this actually is our last example on this set of notes. From America's Families and Living Arrangements, a publication of the U.S. Census Bureau. A joint probability distribution is obtained for the marital status of U.S. adults by gender. So we have horizontally, we have males and females, and then vertically we have single, married, widowed, divorced. And then we have the probabilities over here on the left, or on the right rather, and then we also have probabilities across the bottom. What we want to do is, for part A, determine the probability that the adult selected is divorced given that they are a male. So first, let's consider we're given that the person is male. We want to find the probability that they are divorced given that they are a male. So the way we would figure that out, using the notation that I've put there underneath the names or under each one of the names, we are looking at the probability that they are a male given, wait, did I write this out right? Probability that they're divorced given that they're a male, sorry. Probability that they are divorced given that they are a male. So when we look at the conditional probability table that we're given, this is the same as the probability that they are male and the probability that they are divorced, because this is what our table provides us, divided by the probability that someone is male. Because we don't have enough information from what I'm looking at here to come up with the specific value we're looking at. We can't put this over this and say we're done. So we have to look at the unconditional probabilities. So the probability that they are male and divorced is 0.044. Then the probability that a selected individual is male is the 0.485. And then when we simplify this, we come up with a probability of 0.091. And that is our probability that shows us then that 9.1% of adult males in the U.S. are divorced. Now, part B is going to do something very similar, but for part B, we're looking at the probability that they are male given that the adult is already divorced. So it's the same two criteria, but we're looking at it in a reverse order. Previously, we looked at they're divorced given that they're male. Now we're looking at male given that this person is divorced. So in the terms of the notation, we have the probability of S sub 1 given that it's M sub 4, which is male given that they are divorced, and unconditional probabilities, that would be M4 and S1 divided by the probability that they are divorced. So from our table, the probability that they are divorced and male is 0.044. We already found that one once before. But the probability that they are divorced is 0.014. And then when we simplify that probability, we get 0.423. So it's a totally different value from what we had from example A, but it also has a totally different interpretation. In example A, or part A rather, it was 9.1% of all adult males are divorced. In part B, it's 42.3% of divorced adults are male. So there is a big difference in how we interpret these, and so it matters how you lay out the values when you're setting up the probability notation. That does conclude our set of notes for today. There's your homework problems. I don't think that you'll have too much difficulty with it. I know sometimes it's hard to get used to writing out these probability notations. Just practice with it. And if you have questions, just let me know. I'll talk to you guys soon.